Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. The story of tides, seasons, and planetary tilt is one of the most elegant and subtle narratives in all of astronomy. These phenomena shape the rhythms of life, the flow of oceans, the pulse of weather, and even the development of civilizations. Yet they all trace their origins to simple geometric relationships, gravitational interactions, and the gentle lean of a planet spinning in space. Understanding them requires no complicated mathematics or obscure scientific theories. All it takes is the willingness to imagine Earth in motion, gliding through the cosmos, tugged constantly by the moon, warmed by the sun, and forever turning like a top tilted just slightly off axis. To begin this journey, imagine the Earth as it truly is, not a static sphere, but a world in ceaseless motion. It spins on its axis once every 24 hours, creating the cycle of day and night. It orbits the sun once every year, creating the cycle of seasons. It is locked in a gravitational embrace with the moon, whose pull creates tides that rise and fall with clockwork precision. These motions weave together into an intricate tapestry that governs much of what we experience on the surface. Winds, ocean currents, seasonal climate, biological cycles, and the behavior of ecosystems. Yet none of this would function as it does without one critical detail. Earth is tilted. Its axis sits at an angle of about 23.5 degrees relative to the plane of its orbit around the sun. This tilt might seem like a small detail, something easily overlooked. But it is the single dominant reason our planet has seasons, shifting temperatures, and patterns of light that vary throughout the year. If Earth stood upright with no tilt, every place would experience the same daylight length throughout the year, and seasons as we know them would not exist. Conversely, if the tilt were more extreme, 40 or 50 degrees, the seasons would be far more dramatic, with blazing summers and harsh, dark winters. This tilt also interacts with the gravitational influence of other celestial bodies. For example, the moon stabilizes Earth's tilt. Without the moon, Earth's axis would wobble far more chaotically, causing unpredictable and perhaps extreme changes in climate. But thanks to the moon's steadying presence, our axial tilt varies only slightly over tens of thousands of years, allowing relatively stable conditions in which life has flourished. In this sense, the moon is not only the creator of tides, but also a guardian of climatic stability. When people think of tides, they often imagine waves rushing onto a beach or water rising slowly along a pier. But tides are far more than the movement of the sea. They are giant, planet-wide bulges of water created by the gravitational pull of the moon and, to a lesser extent, the sun. These bulges shift as Earth rotates, giving each coastline 2 high tides and 2 low tides almost every day. The moon's effect is not uniform. It pulls more strongly on the side of Earth closer to it and less strongly on the far side, creating 2 opposite bulges. These bulges are constantly trying to stay aligned with the moon, but because Earth rotates so quickly, the bulges are dragged ahead, slightly offset. That offset has shaped Earth's rotation over billions of years, gradually slowing the planet's spin and pushing the moon farther into space. The sun also creates tides, though weaker than those of the moon. When the sun, moon, and Earth align during full moons and new moons, their gravitational effects combine to create especially large tides known as spring tides. When the sun and moon form a right angle relative to Earth during quarter moons, their effects interfere, producing weaker tides called neap tides. These predictable patterns have influenced fishing, coastal settlement, navigation, and even religious and cultural traditions throughout human history. Just as tides represent a dance between Earth, the moon, and the sun, the seasons represent a dance between Earth's orbit and its axial tilt. Many people misunderstand the reason for the seasons, assuming that summer occurs when Earth is closer to the sun and winter when it is farther away. But this is not true. Earth's orbit is nearly circular. The slight variation in distance contributes only a tiny fraction to temperature changes. Seasons occur because Earth's tilt causes sunlight to strike different parts of the planet at different angles during the year. When the northern hemisphere leans toward the sun, it receives more direct sunlight and experiences summer, while the southern hemisphere leans away, receiving weaker sunlight and experiencing winter. Half a year later, the situation reverses. The change in sunlight angle affects not only temperature, but also the length of daylight. During summer, the sun rises earlier, sets later, and climbs higher in the sky. The days are long and bright, allowing more solar energy to warm the ground, the oceans, and the air. During winter, daylight hours shrink and the sun remains low in the sky, spreading its energy over a larger area and delivering less warmth. This simple geometric effect creates much of the seasonal variation we experience. At the equator, where sunlight is nearly direct all year, seasonal changes are mild. At the poles, where sunlight varies dramatically, the seasons are extreme, even including months of total darkness or continuous daylight. This interplay of tilt, orbit, and light distribution gives rise to countless natural phenomena. It shapes global climate zones, from the tropical rainforest near the equator to the icy deserts of Antarctica. It influences monsoon cycles, jet streams, and the migration patterns of animals. It determines when plants grow and when they enter dormancy. Human cultures have long marked the solstices and equinoxes, the moments of maximum tilt toward or away from the sun, as turning points in the yearly cycle. Ancient monuments such as Stonehenge, Machu Picchu, and the pyramids of Egypt align with the sun's position at these key times, reflecting how deeply seasons have guided human life. But why is Earth tilted at all? The answer lies in its violent childhood. During the early formation of the solar system, Earth was struck by a Mars-sized protoplanet. The collision not only knocked Earth into a tilted orientation, but also created debris that eventually coalesced into the Moon. This event set the stage for billions of years of stable seasons and regular tides. The tilt might have been different had the impact occurred at a different angle or velocity. Earth might have ended up with no significant tilt, or an extreme tilt, or no moon to stabilize it. In this sense, the seasons we enjoy today are the products of ancient cosmic chance. Planetary tilt is not unique to Earth. Many planets in the solar system have axial tilts, some far more extreme than ours. Mars has a tilt similar to Earth's, as giving it familiar seasons, though its thin atmosphere and distance from the sun make them far colder. Saturn's tilt produces striking seasonal changes in the appearance of its rings, which cast shadows across the planet in different ways throughout its 29-year orbit. Neptune's tilt gives it seasons lasting more than 40 years each. But the most dramatic example is Uranus, which lies almost on its side with a tilt of more than 90 degrees. This causes it to experience seasons of extreme light and darkness, where one pole can face the sun continuously for decades, while the other sits in nearly perpetual night. These differences reveal how axial tilt profoundly shapes the environment of each world, influencing atmosphere, climate, and possibly the evolution of any hypothetical life. Earth's tilt and the resulting seasons also interact with the oceans in ways that resonate throughout planetary systems. Seasonal heating and cooling create temperature differences in the oceans, driving currents such as the Gulf Stream. These currents redistribute heat around the globe, moderating climate and making many regions more hospitable. Without the tilt and the varying solar energy it brings, the oceans might be far more stagnant, and weather patterns far more uniform or even inhospitable. Ice ages, too, are connected to shifts in Earth's orbit and tilt. Over tens of thousands of years, variations in axial tilt, the shape of Earth's orbit, and the wobble of its rotational axis combine to create cycles of warming and cooling known as Milankovitch cycles. These cycles have triggered the advance and retreat of ice sheets, shaping continents and ecosystems throughout the planet's history. Even life itself has been shaped by tides, seasons, and tilt. Ocean tides create intertidal zones, environments that alternate between wet and dry, hot and cool, submerged and exposed. These zones are rich in biodiversity and may have played a crucial role in the emergence of life from the oceans onto land. Seasonal changes drive migration and reproduction patterns, influencing everything from the flowering of plants to the movement of whales, birds, and insects. Human societies depend on seasonal cycles for agriculture, hunting, and resource management. Calendars were originally designed to track the seasons, ensuring that people knew when to plant crops or prepare for winter. Without the predictable rhythm created by Earth's tilt, such planning would have been far more difficult. The moon's effect on tides has also influenced the evolution of life. The gentle rise and fall of water along coastlines creates habitats that encourage adaptation to changing conditions. Some scientists believe that early organisms may have first ventured onto land by following receding tides. The tidal cycle also affects the behavior of many marine species, cueing reproduction, feeding, and migration. Even today, coastal communities live in harmony with the tides, using their knowledge to navigate waters, harvest resources, and protect against flooding. Earth's tilt also affects its orientation in space over long timescales. The planet slowly wobbles like a spinning top in a movement called precession. This wobble takes about 26,000 years to complete a full cycle. Precession changes the timing of the seasons relative to Earth's orbit, which can strengthen or weaken seasonal effects depending on the hemisphere. Another slow movement, called nutation, causes small oscillations in the tilt angle. These long-term cycles contribute to changes in Earth's climate, especially when amplified by feedback mechanisms such as ice formation, atmospheric composition, and ocean circulation. The sun also plays a role in shaping Earth's environmental rhythms. Solar radiation varies slightly over time due to the sun's magnetic cycles. When the sun is more active, some regions may experience warmer conditions. When it is less active, slight cooling may occur. These solar variations do not create seasons or tides, but they do modulate climate, sometimes in combination with Earth's tilt and orbit. The most well-known example is the Little Ice Age, a period of cooler temperatures from the 14th to the 19th centuries, which may have been influenced partly by a decrease in solar activity known as the Maunder minimum. Every part of this system, tides, tilt, seasons, moon, orbit, intertwines with the others. The gravitational pull that creates tides also stabilizes Earth's tilt. The tilt that creates seasons also affects patterns of wind and ocean circulation. The orbit that brings Earth closer or farther from the sun contributes subtly to temperature differences. Together, they form a delicate balance that makes Earth uniquely habitable. If any component were significantly different, the planet might be far less welcoming. A world with no tilt might lack seasonal diversity, reducing ecological niches. A world with extreme tilt might suffer from harsh, unpredictable climate. A world without a large moon might wobble chaotically, creating unstable conditions for life. A world with weaker tides might have evolved very differently, or perhaps not at all. These connections illustrate how deeply our planet's behavior is tied to the mechanics of the entire solar system. Studying tides and seasons is not simply about understanding water or temperature. It is about appreciating the cosmic context in which Earth exists. Every sunrise and sunset, every summer and winter, every tide that ebbs and flows is a reminder of Earth's constant motion and the forces exerted upon it by the moon and the sun. These phenomena show that even the most ordinary experiences of daily life are governed by celestial mechanics operating at grand scales. Earth's journey through space continues to shape tides, seasons, and the effects of planetary tilt in ways that influence every aspect of the environment. To understand these relationships more deeply, it helps to visualize Earth as part of a dynamic gravitational network. The sun's immense mass creates the dominant gravitational force in the solar system, holding Earth and the other planets in their orbits. The moon, though much smaller, has a powerful impact on Earth because it is so close. These gravitational interactions are not static. They create ongoing movements, flexing, stretching, and shaping Earth's systems. The tides themselves are more complex than simply the rise and fall of water. They influence the ocean at every depth, stirring and mixing water layers that would otherwise remain relatively isolated. This mixing effect helps distribute nutrients and heat throughout the world's oceans. Without tides, the deep sea would be far more stagnant, with less oxygen circulation and fewer opportunities for marine life to thrive. Tides also influence the formation of estuaries and wetlands, which are among the most productive ecosystems on the planet. These areas form where fresh water from rivers meets salty ocean water, creating nutrient-rich habitats ideal for spawning fish, migratory birds, and countless other species. Tide-driven processes transport sediments, reshape coastlines, and form deltas, landscapes that have become home to millions of people. In addition to their biological role, tides have shaped human history in practical ways. Early civilizations relied on tides for fishing and transportation, developing calendars and rituals based on lunar cycles. The construction of ancient ports, the timing of maritime trade, and even military strategies have all been influenced by the tides. The development of tidal mills during the Middle Ages harnessed tidal energy long before modern technologies. Today, the potential for tidal power is being explored as a renewable energy source, taking advantage of the predictable rhythms of the moon's pull. As we turn back to seasons, we find that their influence extends beyond climate and ecosystems. Seasons help regulate the carbon cycle on Earth. During spring and summer, plant life in the northern hemisphere, where most of Earth's landmass is located, absorbs vast amounts of carbon dioxide through photosynthesis. This causes atmospheric carbon dioxide levels to dip slightly. In autumn and winter, when plants go dormant and leaves fall and decay, carbon dioxide levels rise again. This seasonal breathing of the biosphere creates a rhythmic oscillation in the global carbon cycle, visible today in precise atmospheric measurements. It is a reminder that Earth's tilt affects not only temperature, but also the chemistry of the atmosphere and the functioning of life itself. Another important factor in understanding seasons is the concept of solar insolation, or the amount of sunlight that reaches a given area. Insolation varies based on latitude, time of year, and the tilt of Earth's axis. This variation drives weather patterns, monsoons, and climate zones. Equatorial regions receive relatively consistent sunlight year-round, creating warm, humid conditions that support rainforests. Mid-latitudes experience stronger seasonal contrasts, supporting deciduous forests, grasslands, and agricultural regions. Polar areas, with their dramatic shifts from continuous daylight to continuous darkness, remain cold and barren, shaped by glaciation and permafrost. The distribution of sunlight also influences atmospheric circulation. As warm air rises near the equator, it moves toward the poles, cools, and eventually sinks, creating large-scale circulation cells. These cells, known as Hadley, Ferrel, and polar cells, generate the trade winds, westerlies, and polar easterlies that define global wind patterns. The tilt of Earth modulates the strength and position of these circulation systems throughout the year. This in turn affects rainfall patterns, storm tracks, and even the intensity of tropical cyclones. Without Earth's tilt, atmospheric circulation would be far more symmetrical and predictable, potentially eliminating many of the weather patterns that define the character of our planet. Exploring further, seasons interact with the oceans as well. Seasonal heating causes water to expand, creating changes in sea level that complement tidal forces. In some regions, such as the Indian Ocean, these seasonal differences are so pronounced that they drive massive monsoon systems. During the summer, the land heats more quickly than the ocean, creating low-pressure zones that pull in moist air from the sea. This results in heavy rainfall, essential for agriculture, but also capable of causing devastating floods. In winter, the situation reverses, and drier air flows outward from the landmass. Such dynamics exist because of the way seasonal temperature differences redistribute energy across the planet. Without the tilt that creates seasons, monsoon systems might not exist at all, fundamentally changing the distribution of life and human populations. The tilt of a planet is determined by a combination of factors, including initial formation conditions, collisions with other bodies, and gravitational influences from nearby planets or moons. In Earth's case, the early collision that formed the moon was a defining event, but planetary tilt can evolve over time. Mars, for example, lacks a large moon to stabilize its axis, causing its tilt to vary widely over millions of years. These fluctuations lead to extreme climate swings, including the periodic melting of polar ice. Saturn's moon Titan experiences seasons because of Saturn's tilt, and its thick atmosphere and hydrocarbon lakes respond to seasonal changes much like Earth's hydrological cycle does. Even distant Pluto has seasons, though its elongated orbit and unusual tilt create long, subtle cycles lasting more than 2 centuries. Understanding planetary tilt in other worlds helps scientists imagine what climates might be like on exoplanets, worlds orbiting other stars. When astronomers study exoplanets, one of the most important factors they consider is axial tilt. A planet with no tilt might have a relatively uniform climate, while one with an extreme tilt could face intense, potentially uninhabitable seasonal changes. A stable tilt indicates the possible presence of a moon or certain orbital configurations. By studying these characteristics, scientists can assess the likelihood of life-supporting environments on worlds far beyond our solar system. Returning to Earth, the tilt also plays a critical role in shaping the polar regions. During summer, one pole receives continuous daylight, causing temperatures to rise and ice to melt. During winter, the same region receives no sunlight, leading to intense cooling and the growth of sea ice. These changes influence global albedo, the measure of how much sunlight Earth reflects into space. Ice reflects far more sunlight than liquid water or land, creating feedback loops. When ice melts, more sunlight is absorbed, warming the planet further. When ice expands, more sunlight is reflected, cooling the planet. Earth's tilt governs the timing of these cycles, creating long-term stability punctuated by ice ages. Even small shifts in tilt, combined with orbital variations, can trigger significant climate transitions. One fascinating interaction between tides and seasons occurs in the Arctic. As the sun returns after months of darkness, the combination of warming temperatures and tidal forces begins to break up sea ice. Tides help churn the water beneath the ice, weakening it and encouraging melting. In coastal areas of the Arctic, tides can lift ice sheets, cracking them and contributing to seasonal changes in ice coverage. This process affects wildlife such as seals, walruses, and polar bears, which rely on the presence and movement of sea ice for hunting and breeding. Migratory species time their journeys with both seasonal changes and tidal cues, demonstrating how interconnected these systems are. If we imagine Earth without its tilt, the consequences would be profound. The equator would always be the hottest region, the poles permanently cold, and the mid-latitudes dominated by stable, unchanging weather patterns. Deciduous forests might not develop. Many species that rely on seasonal cues would never evolve, and agriculture, as we know it, would not exist. Civilizations that depend on predictable growing seasons would face a world with far different opportunities and challenges. Conversely, if Earth's tilt were extreme, the planet might experience enormous seasonal swings. Summers could bring scorching heat and long days even at high latitudes, while winters could plunge those same regions into deep, prolonged darkness. Such conditions would strain ecosystems, limit habitable regions, and create challenges for the emergence of complex life. In addition to axial tilt, a planet's rotational speed affects how tides and seasons manifest. A faster spinning Earth would experience stronger Coriolis forces, altering wind patterns, ocean currents, and weather systems. Tidal bulges would also be positioned differently relative to the moon, potentially leading to different patterns of coastal flooding or mixing in the oceans. A slower spinning Earth, on the other hand, would have longer days and nights, impacting temperature cycles and possibly intensifying daily temperature extremes. The interaction between rotation, tilt, and solar exposure defines the daily and annual rhythms that life has adapted to. The interconnectedness of these systems becomes even more apparent when considering how they influence long-term geological processes. Tides create friction that slightly deforms Earth's crust and mantle. Over millions of years, this tidal flexing converts rotational energy into heat, subtly affecting the planet's interior. Although the effect is small compared to heat from radioactive decay, it contributes to the complex energy balance that shapes Earth's geology. Seasonal variations, too, influence geological systems. The weight of seasonal snow and ice accumulation can depress the crust, while melting can cause it to rebound. Rivers swell with seasonal meltwater, eroding landscapes and transporting sediments that shape coastlines and deltas. All these processes remind us that wishes, seasons, and planetary tilt are not isolated concepts, but deeply interwoven forces sculpting the Earth over short and long timescales. They govern the rhythms of oceans and atmospheres, the movement of tectonic plates, the behavior of ecosystems, and the evolution of life. More than that, they influence human culture, agriculture, transportation, and understanding of time itself. The very structure of human society, from festivals marking solstices to economic systems built on agricultural cycles, is rooted in these celestial mechanics. Earth's story becomes even richer when we look more closely at how tides, seasons, and planetary tilt influence not just the world as a whole, but specific regions, ecosystems, and even individual species. The interplay of these forces creates countless variations in climate, habitat, and environmental rhythm. Each coastline experiences tides differently depending on the shape of the land, the depth of the seafloor, and the alignment of the moon and sun. In some regions, such as the Bay of Fundy in Canada, the shape of the coastline creates some of the highest tides in the world, rising and falling by more than 15 meters. In contrast, in the Mediterranean Sea, the restricted connection to the open ocean results in only small tidal changes. These differences illustrate how global forces can produce highly localized effects. The shape of coastlines and ocean basins plays a major role in amplifying or reducing tides. When tidal waves move into narrow or shallow regions, the water level can rise dramatically. These amplified tides have shaped human settlements, creating rich fishing grounds and fertile plains. But they can also bring challenges. Coastal erosion, storm surges, and flooding are strongly influenced by tides, especially when combined with seasonal weather patterns. In monsoon regions, the combination of high tides and heavy rainfall can cause devastating floods that reshape landscapes and displace communities. Understanding these interactions has become increasingly important as climate change raises sea levels and alters weather patterns. Seasons, too, create complex regional variations. The monsoons of South Asia, the Mediterranean climate of California, the long winters of Siberia, and the equatorial rains of the Amazon all exist because of Earth's tilt and its annual journey around the sun. In some regions, seasonal changes are subtle, noticeable only through shifts in rainfall or the blooming of certain plants. In others, the contrast is extreme, such as the intense dry and wet seasons of East Africa that drive great migrations of wildebeest and zebras. These migrations depend on the movement of rain, which in turn depends on the position of the sun in the sky. Life evolves around these rhythms, adapting to take advantage of seasonal opportunities. Some species are so attuned to seasons that even slight changes can disrupt their life cycles. Birds time their migrations to coincide with seasonal food availability. Plants depend on seasonal sunlight and temperature changes to trigger flowering, fruiting, and seed dispersal. Many insects synchronize their life cycles to match seasonal patterns, emerging at specific times to feed, reproduce, or avoid predators. If Earth's tilt were to change significantly, these patterns could be disrupted. Even small deviations in the amount of daylight or peak seasonal temperatures would have cascading effects on ecosystems. This sensitivity underscores the deep connection between life and the celestial mechanics that govern Earth's environment. Another aspect of seasonal influence is the way it shapes human behavior. Societies throughout history develop cultural traditions, agricultural cycles, and economic systems based on the predictable arrival of seasons. The solstices and equinoxes were celebrated as sacred events, marking turning points in the year. Farmers relied on seasonal cues to plant and harvest crops. Hunters and gatherers followed migratory animals or the seasonal availability of resources. Even today, modern societies are shaped by seasonal changes. From holiday traditions to energy consumption patterns, tourism cycles, and the timing of school years. The tilt of Earth's axis plays an equally important role in shaping human geography. Regions at higher latitudes experience shorter growing seasons, influencing which crops can thrive and how societies develop. The long winters of Northern Europe encourage the development of storage systems and preservation techniques, shaping cultural practices. In contrast, tropical regions with consistent sunlight supported year-round agriculture and biodiversity. The tilt of Earth does more than create weather patterns. It influences the development of civilizations, economies, and cultural identities. Earth's tilt also interacts with atmospheric and oceanic circulation to create phenomena like the jet stream, a high-speed ribbon of air that flows across the upper atmosphere. The position and strength of the jet stream shift with the seasons as temperature gradients between the equator and poles change. This powerful air current guides storms, influences temperature extremes, and affects rainfall distribution. Seasonal shifts in the jet stream can bring heat waves, cold snaps, or prolonged storms. Understanding these patterns is critical for predicting weather and preparing for seasonal impacts on society. The relationship between Earth and the Moon adds another layer to the story. The Moon's gravitational influence, combined with Earth's rotation, creates tides that shape coastlines and influence marine ecosystems. The gravitational interaction also affects Earth's rotation rate. The tidal bulges raised by the Moon create friction that slows Earth's rotation over time. As Earth slows, angular momentum is transferred to the Moon, causing it to move gradually farther away. The Moon currently recedes from Earth at about 3.8 centimeters per year. Over millions of years, this gradual separation changes the length of Earth's day and the strength of tides. In Earth's distant past, days were much shorter, and tides were stronger. Stronger tides would have created more intense mixing in the oceans, influencing early life. As the Moon continues to drift outward, tides will become weaker, and Earth's rotation will continue to slow. These changes will gradually alter the dynamics of Earth's climate, though the effects unfold over such long timescales that they are almost imperceptible on human timescales. Seasonal and tidal cycles also influence Earth's magnetic environment. Although the tilt of the magnetic axis differs from the tilt of the rotational axis, the interaction between solar radiation, Earth's magnetic field, and atmospheric circulation creates patterns such as auroras. Seasonal variations in sunlight and atmospheric composition affect the strength and distribution of these displays. During periods of high solar activity, charged particles from the sun interact with Earth's magnetosphere, creating brilliant displays of light near the poles. The visibility and intensity of auroras can vary with the seasons, influenced by changes in atmospheric density and the orientation of Earth relative to the sun. Another fascinating aspect of Earth's tilt is how it influences the distribution of ecosystems across the globe. Climate zones, from tropical rainforests to temperate forests, grasslands, deserts, and tundras, exist because of the way sunlight is distributed across the planet. The equator receives the most direct sunlight, creating warm, humid conditions that support dense vegetation. Moving toward the poles, sunlight becomes less direct, temperatures drop, and ecosystems shift accordingly. In mid-latitudes, where seasonal variations are greatest, deciduous forests and grasslands thrive. These regions experience distinct periods of growth, dormancy, and renewal that shape the biodiversity found there. The tilt also influences the distribution of permafrost, permanently frozen ground found in polar and subpolar regions. Seasonal changes in sunlight cause the upper layers of permafrost to thaw in summer, creating wetlands and releasing methane, a powerful greenhouse gas. These processes are closely tied to Earth's seasonal cycles. If the tilt or climate conditions change significantly, the stability of permafrost could be affected, with global consequences for climate and ecosystems. Expanding our perspective beyond Earth, tides and seasons on other planets offer clues about the diversity of environments that might exist in the universe. On Jupiter's moon Europa, tidal forces from Jupiter generate heat within the moon's interior, maintaining a subsurface ocean beneath an icy crust. This tidal heating could create conditions suitable for life. Similarly, on Saturn's moon Enceladus, tidal flexing produces jets of water vapor and ice that erupt from the moon's south pole. These plumes contain organic molecules, hinting at a potentially habitable environment beneath the surface. These examples show that tides are not merely a terrestrial phenomenon, but a universal process that can shape entire worlds. The seasons of Mars are shaped by its tilt and elliptical orbit. Because Mars has a tilt similar to Earth's, it experiences familiar seasonal patterns. However, its elongated orbit means that one hemisphere experiences more extreme seasons than the other. Dust storms, temperature variations, and atmospheric pressure changes on Mars follow seasonal cycles. Scientists study these patterns to understand Mars's climate history and assess its potential for supporting life. Understanding the interplay of tilt, orbit, and climate on Mars also provides insights into Earth's own climate system. Saturn's tilt influences the appearance of its rings. As Saturn orbits the Sun, the rings change orientation relative to Earth. Sometimes they appear wide open, other times they nearly disappear from view when seen edge-on. These changes reflect the planet's tilt and provide a visual reminder of how axial inclination affects the appearance and behavior of celestial bodies. Even gas giants experience seasons, though their effects are more subtle due to their distance from the Sun and thick atmospheres. Uranus presents one of the most extreme examples of axial tilt. With a tilt of more than 90 degrees, the planet essentially rolls around the Sun on its side. This creates extraordinary seasons, with each pole experiencing decades of continuous sunlight followed by decades of darkness. The unusual tilt likely resulted from a massive collision during Uranus's early history. This dramatic orientation challenges our understanding of climate systems, offering a glimpse of how different worlds can be when shaped by unique cosmic events. Returning to Earth, the combined effects of tides, seasons, and tilt also play a role in shaping long-term climate trends. The interaction of Earth's axial tilt with its orbital cycles contributes to glacial and interglacial periods. When the tilt is smaller, seasonal contrasts diminish, allowing ice sheets to grow. When the tilt is larger, more intense seasonal heating can melt ice and warm the planet. These cycles unfold over tens of thousands of years and have left a clear imprint in geological records. Understanding these cycles helps scientists predict future climate changes and assess the potential long-term impacts of human activity. Meanwhile, the natural interplay of tides and seasons continues to influence everyday life. Coastal ecosystems rely on tidal rhythms to maintain balance. Seasonal changes guide agricultural practices, wildlife migrations, and resource availability. Weather patterns shift with the tilt of Earth, bringing changes in temperature, precipitation, and daylight. Even the rhythms of human culture, from holidays to work schedules, are shaped by these celestial patterns. Earth's environment is a tapestry woven from the rhythmic forces of tides, seasons, and planetary tilt. But the story grows even deeper when we consider how these forces shape biological cycles, climate evolution, and even the long arc of Earth's geological history. These cycles do not merely act on the world, they create the very conditions that allow life to flourish, adapt, and evolve. As we look more closely at the influence of tides on marine life, we discover that entire ecosystems depend on the predictability and timing of tidal movements. Intertidal zones, the regions between high and low tide, are among the most dynamic and challenging habitats on Earth. Organisms that live here, barnacles, mussels, sea stars, crabs, seaweeds, must endure periods of submersion followed by exposure to air, fluctuating temperatures, and powerful waves. Their life cycles are synchronized with the tides, guiding feeding, reproduction, and growth. Some species release their gametes only at specific points in the tidal cycle, ensuring that their offspring have the greatest chance of survival. Others migrate vertically or horizontally with the tides, taking advantage of nutrient flows or avoiding predators. These ecosystems would not exist without the gravitational interplay of Earth and the Moon. Tidal rhythms extend far beyond coastal areas. In the deep ocean, internal tides propagate through water layers, influencing nutrient cycling and the behavior of deep-sea organisms. These internal waves can travel thousands of kilometers, breaking on underwater mountain ranges and continental slopes. When they break, they mix cold, nutrient-rich deep water with warmer surface waters, supporting plankton growth. This productivity forms the foundation of oceanic food chains and influences global carbon cycles. Tides, therefore, play a subtle yet crucial role in regulating the health and stability of marine ecosystems across the planet. Seasons, likewise, exert profound influence on life. The changing angle of sunlight triggers the growth and dormancy cycles of plants, which in turn provide food and habitat for countless animals. In temperate regions, deciduous forests burst into life each spring, creating a surge of biological activity. Fruits and seeds ripen in summer and autumn, providing nourishment for migrating birds, hibernating mammals, and insects preparing for winter. In tropical regions, wet and dry seasons structure the movement of animals and the timing of plant reproduction. Forests shed leaves in the dry season to conserve water, while monsoon rains trigger explosive growth. The rhythm of seasons creates a pulse of life that shapes biodiversity and ecological balance. Even marine plants like phytoplankton respond to seasonal variations in sunlight and temperature. Spring blooms of phytoplankton in the oceans trigger massive increases in zooplankton populations, which support fish, seabirds, and marine mammals. These seasonal blooms play a key role in absorbing carbon dioxide from the atmosphere, helping regulate Earth's climate. Without the tilt-driven changes in sunlight that mark the seasons, these critical processes would be altered or absent. The influence of planetary tilt extends even into deep time, shaping the evolution and distribution of life. Fossil records show how past changes in Earth's tilt and orbit contributed to ice ages, mass migrations, and shifts in biodiversity. During periods of reduced tilt, ice sheets expanded, sea levels dropped, and climates became cooler and more uniform. These conditions encouraged the spread of grasslands and the evolution of grazing mammals. During periods of increased tilt, seasonal variations intensified, creating more diverse habitats and promoting evolutionary innovation. The cyclic nature of these changes created opportunities for species to adapt or move, contributing to the complex web of life that exists today. In human history, the interplay of tides, seasons, and tilt shaped the development of technology and science. Ancient mariners used tidal patterns to navigate coastal waters, timing their voyages with the phase of the moon. Understanding tides became essential for fishing, trade, and defense. Priests and astronomers tracked the movement of the sun to predict solstices and equinoxes, developing early calendars. The ability to measure seasons accurately allowed civilizations to plan agricultural activities, enabling the rise of stable societies. Stonehenge, the pyramids, Chichen Itza, and countless other ancient structures were aligned with seasonal celestial events, reflecting humanity's deep connection to Earth's axial tilt and orbit. As scientific understanding grew, scholars realized that the tilt of Earth was not fixed. Subtle changes caused by gravitational interactions with the sun and moon alter the tilt over tens of thousands of years. These variations influence climate cycles known as Milankovitch cycles, which combine changes in tilt, orbital shape, and axial wobble. These cycles have driven ice ages and warm periods throughout Earth's history. They demonstrate that Earth's climate system is interconnected with celestial mechanics. Human activities now add another layer to this system, influencing climate on much shorter timescales. The relationship between tides and seasons also affects Earth's water cycle. Seasonal melting of snow and ice feeds rivers, replenishing freshwater supplies and shaping landscapes. Tides influence the mixing of river water with ocean water, affecting nutrient levels and sediment transport. These processes create fertile floodplains and estuaries that support agriculture and biodiversity. Civilizations such as those along the Nile, Tigris, Euphrates, and Mekong rivers developed around these reliable seasonal and tidal cycles. Even today, agriculture in many parts of the world depends on seasonal rains, snowmelt, and river flows influenced by Earth's axial tilt. Climate patterns such as El Niño and La Niña also interact with seasonal cycles. These phenomena arise from shifts in ocean circulation and atmospheric pressure in the Pacific Ocean. Although not directly caused by Earth's tilt, their effects are modulated by seasonal changes in sunlight and temperature. During El Niño events, warm water spreads across the Pacific, altering rainfall patterns and causing droughts, floods, and storms. Seasonal changes either amplify or moderate these impacts, demonstrating how interconnected Earth's climate systems are. Another remarkable influence of tilt and seasons lies in the behavior of the polar regions. In the Arctic, continuous summer sunlight melts sea ice, creating open waters that absorb more sunlight and accelerate warming. In winter, the absence of sunlight allows ice to grow, increasing reflectivity and cooling the region. These seasonal shifts form one of the most important climate feedback loops on Earth. And as climate warms, summer ice melts earlier and more extensively, reducing reflectivity and increasing heat absorption. This feedback doesn't just affect the Arctic, it influences global weather patterns, jet stream behavior, and ocean circulation. Similar processes occur in Antarctica, where the tilt-driven alternation of sunlight shapes the growth and retreat of sea ice around the continent. Tides also play a role in polar regions by influencing the movement and breakup of sea ice. Tidal flexing can fracture large ice sheets, creating leads and polynyas, open water areas surrounded by ice. These openings are critical habitats for marine life and serve as breathing holes for seals and hunting grounds for polar bears. In Antarctica, tides influence the stability of ice shelves by flexing them as the ocean rises and falls. This flexing can weaken structural integrity over time, contributing to ice shelf collapse and the release of glacial ice into the ocean. The interaction between tilt, seasons, and tides becomes even more intriguing when we consider the long-term evolution of Earth's orbit. Over millions of years, interactions with other planets cause Earth's orbit to shift slightly. These slow changes influence the distribution of sunlight across latitudes, altering the intensity of seasons. Combined with variations in tilt, these orbital shifts have shaped Earth's climate cycles and influenced major transitions, such as the onset of ice ages. The record of these cycles is preserved in ice cores, sediment layers, and fossil distributions. In addition to Earth's orbit, the rotation of the planet also changes slowly over time due to tidal friction. As Earth's rotation slows, days become longer. Hundreds of millions of years ago, a day on Earth lasted only 20 hours. This gradual lengthening of the day influences the daily cycle of sunlight and could have affected the behavior and evolution of early life. Photosynthetic organisms, for example, may have adapted to shorter or longer periods of daylight, depending on the era in which they evolved. This connection between tides and the length of the day shows how even seemingly small astronomical processes can influence the development of life. Looking to the future, the ongoing interplay of tides, seasons, and tilt will continue to shape Earth's climate and environment. As the moon moves gradually farther away, tidal forces will weaken. Earth's tilt may vary slowly over tens of thousands of years, altering seasonal intensity. Human influence on climate will interact with these natural cycles, creating uncertainties and challenges. Understanding these relationships helps us prepare for future changes and appreciate the complexity of the systems that sustain life. At the same time, studying other planets helps us understand what makes Earth unique. Venus, with little axial tilt, experiences almost no seasons. Its slow rotation and thick atmosphere create a stagnant, hostile environment dominated by greenhouse gases. Mars, with a tilt similar to Earth's but lacking a stabilizing large moon, experiences dramatic climate swings over long timescales. Gas giants like Jupiter and Saturn experience subtle seasons, but their immense atmospheres respond differently to solar input. Uranus and Neptune show how extreme tilts, or distant orbits, can create environments fundamentally different from Earth's. These comparisons highlight the delicate balance of factors that create Earth's livable climate. Our moderate tilt gives us diverse seasons without extreme swings. The presence of the moon stabilizes Earth's axis, keeping seasonal changes predictable. Tidal forces shape oceans and influence the climate system. The combination of these effects makes Earth one of the most life-supporting environments we know of in the universe. Even the cultural aspects of human civilization are intertwined with these celestial rhythms. Literature, art, mythology, and religion all draw inspiration from the moon, the sun, the ocean's tides, and the changing seasons. Poets wrote of the melancholy of autumn, the renewal of spring, the stillness of winter, and the brightness of summer. Farmers and ancient astronomers built monuments aligned with solstices. Entire calendars were developed to track the lunar cycle. These cultural expressions reflect an intuitive understanding of the forces that govern our world. As we deepen our scientific understanding, we enhance our appreciation of these cosmic rhythms. The rise and fall of tides, the tilt of Earth's axis, the journey around the sun, these are not abstract astronomical concepts, but the living heartbeat of our planet. They shape the air we breathe, the food we eat, the climate we experience, and the patterns of life all around us. They connect every organism to the motions of celestial bodies across vast reaches of space. The deeper we explore the interplay between tides, seasons, and planetary tilt, the more we discover that these phenomena are not isolated curiosities, but intimately connected expressions of a planet's internal and external rhythms. A world's tilt reshapes its sunlight, its heat flow, its atmospheric circulation, and its ecological patterns, while tides sculpt shorelines, moderate climates, and interact with orbital mechanics in ways that can either stabilize or destabilize a planet across cosmic time. These forces form a kind of planetary choreography, slow, graceful, and powerful, unfolding across billions of years, each movement leaving a signature on the landscapes and life forms that emerge. On Earth, this choreography has created the world we know. Oceans that pulse to the pull of the moon and sun, polar regions that alternately sleep and awaken, forests and grasslands whose rhythms are tuned to the march of seasonal light, and a climate system that balances energy through the tilt of the axis and the rotation of our sphere. Even the geology of Earth carries the imprint of these cycles. Countless tide-generated layers in ancient rocks record a story of shorter days and faster spins. Fossil corals preserve the distant past when the moon hovered closer and the tides were stronger. Sedimentary rhythms trace ancient seasons, proving that long before humans existed, the planet was already turning through cycles of light and darkness with astonishing precision. Much of what we understand about planetary tilt and why it matters comes from comparing Earth with its neighbors. Venus, with almost no seasons and barely any tilt, stands as a cautionary example of how a planet without axial variation can lock itself into extreme atmospheric conditions. Mars, with its exaggerated swings and tilt, shows how instability can transform a world from warm and semi-wet to frozen and windswept. Uranus, rolling on its side, demonstrates how radically different a planetary environment can be when the tilt is pushed to an extreme. Neptune and Jupiter remind us that giant planets experience seasons too, though gentler ones, and their internal heat often overwhelms the seasonal changes from starlight. And Mercury and the Moon show the opposite case. Worlds with essentially no axial tilt at all, where the sun's position barely shifts in the sky, and where timeless shadows hide ice even near the inner reaches of the solar system. All these worlds combine into a broader lesson. Seasons are not guaranteed, and tides are not universal in the way we experience them. They are the result of particular alignments, particular histories, particular accidents of formation. Remove the moon, adjust the tilt, move a planet farther from or closer to its star, and the entire balance changes. A world with gentle seasons may become a world of violent climatic cycles. A world with mild tides may become a world ravaged by orbital stress. A world with predictable climates may become a world whose surface freezes and thaws in chaotic rhythms. The remarkable thing is that even small differences can cascade. A shift of just a few degrees in tilt can alter monsoon patterns, affect the formation of deserts, or change ocean currents. A slight adjustment in tidal forces can modify the transfer of heat across the globe, or alter how a planet's rotation slows. Over millions of years, these subtle effects accumulate into profound environmental transformations. The mechanisms seem simple: gravity, sunlight, rotation, but the outcomes are endlessly complex. And because these forces operate slowly on human timescales, it is easy to take them for granted. We experience them as ordinary. The tide comes in and out. The seasons turn as they always do. Daylight shortens and lengthens every year, and the moon glides through the night sky. Yet each of these motions is a delicate balance of forces across enormous distances. The moon must remain gravitationally locked in a stable orbit. Earth must maintain a tilt that is neither too small nor too large. The sun must continue to dominate the gravitational architecture of the solar system, but not pull Earth's orbit into extreme eccentricity. We live in a narrow band of conditions where these cycles reinforce stability instead of chaos. Looking beyond our solar system, astronomers now see that many exoplanets orbit stars and configurations where tides, seasons, and tilt would create environments far more exotic than anything we know. Some worlds are tidally locked, with permanent day sides and night sides. Some orbit red dwarfs so closely that their temperatures may oscillate wildly as flare activity changes the radiation they receive. Some have eccentric orbits that create intense mega-seasons, where climate varies not just gently over the course of a year, but violently with every passage around their star. Others may experience tidal heating strong enough to melt crusts, maintain subsurface oceans, or even trigger global volcanism. and a few may have stabilizing moons or moderate tilts that allow them to host climates surprisingly Earth-like despite very different stellar environments. These discoveries push us to rethink what it means for a world to be habitable. It may not be enough for a planet to sit in the so-called habitable zone. It must also have the right tilt, or the right mechanism for keeping that tilt from drifting too much. It must have the right tidal interactions, or the right combination of rotation and orbital distance to prevent locking or brutal tidal extremes. Habitability in this sense becomes a multidimensional question. It is not defined by temperature alone, but by the variability of temperature. Life often thrives not where conditions are constant, but where they fluctuate in predictable rhythms. Seasons provide that rhythm. Tides provide it too. Tilt ensures that sunlight moves across the surface in ways complex enough to allow ecosystems to adapt and evolve. This perspective reshapes how we view Earth itself. Our world's stability is not a static gift. It is an ongoing dynamic between forces that constantly push and pull. The moon recedes. Earth's rotation slows. The continents move. The atmosphere evolves. The tilt precesses. The oceans reshape their basins. Even the distribution of mass on Earth affects how the axis wobbles and how the seasonal cycle subtly shifts. At a glance, these changes appear insignificant, but over the eons, they accumulate into new climates, new seas, new ecosystems, and new chapters of planetary history.